Hey YouTubers, this is the Engineer channel, and we're going to be talking about engines and engine related stuff, motors, basically whatever else comes through this workshop of mine. On this beautiful February night, I've chosen a nice topic, and it's one of the weed whackers that I took apart in the past. I bought this for a particular reason, and we're going to be talking about this right now. So these are all the parts from the weed whacker. I took it apart. Mostly what you see here are the engine parts, and this is a Ryobi 4-cycle. It's a c430, and there's the Ryobi brand. I basically bought these because I wanted to see where the industry is today and what is the best the industry can provide for 150 bucks basically. What you're looking at here, this engine, it's a 4-stroke engine with the attachment, basically the weed whacking attachment. It's 150 bucks. That's it. My particular interest was how did they lay out the valve train, the camshaft, and how did they oil the internal parts of the engine. So back around 2013 I put an ad in Craigslist, and I was basically looking for a 4-stroke weed whacker. It's okay if it doesn't run, and sure enough someone found me, and I ended up buying this. And the owner said that it's not running. It was running in the past, but it's not operational. It didn't show any oil stains or any other kind of degradation on the outside. So I basically took it apart, and I've had it apart ever since then. This is the engine housing, and this engine housing, as you can see, the cylinder right here in the middle, this is the cylinder, this is the crankshaft housing, and this is basically the cylinder head. Everything is one piece. Okay, this is all most likely die-cast aluminum. As far as it goes, I don't see any kind of markings on it. The interesting thing about it is it has some kind of coating on the inside. This is that NicoSeal or CaniSeal coating that's been pretty widespread after the 2000s. Originally the patent was owned by Mahle Corporation. I think it's in Germany or maybe Austria. And what this is, it's some kind of carbide or some kind of hard particle encased in a nickel matrix. So basically the nickel holds it together, and you got some kind of hard particles, and it's really small size. And what they do is they plate the innards of the cylinder with it, and so they can basically end up with a aluminum cylinder, and it doesn't need a liner. Traditionally the cylinders were cast iron cylinders, and later what they had is aluminum cylinders with cast iron liner. Let me show a couple examples. Okay, so these are a couple other examples, and I have one here that's cut in half. So this one, as you can see, is a cast iron cylinder. This is from a Honda Cub copy from China. You can see it says right here 107 cc, and then there's some kind of marking for the manufacturer. This entire cylinder is basically cast iron, so there's no liner here inside. What we had in the past, especially for two-stroke engines, the external housing was made out of aluminum, and then the liner was cast iron, and the cast iron liner was pressed in, usually from the top. So when you saw people doing tuning, they pressed out the liner and then they cut the holes inside for two-stroke engines a little bigger, and then they can reassemble it. Now this is another version, which is basically an aluminum housing, and you have a cast iron liner. So I took one of these apart, and this is how it looks like on the inside. So you can clearly see that this is aluminum, cast iron, same on the other side. This one, the skirt on the bottom here broke off when I was trying to press out. Obviously I didn't know that the liner is not a press fit. What they did here is the liner is cast, and then the outside surface of the liner is really rough. And what they do is they put it in a mold, and they mold the aluminum over it, and that's how they end up with this cylinder shape. Now this is the same cylinder, but it's the other side. I cut it in half so I can look into the microstructure and I can see how it's being put together. But right here you can see how rough that surface is. So this has two benefits. The first benefit is this is really a rough surface, so it improves the thermal. What you have is you generate heat inside the cylinder. That heat wants to travel across and then being dissipated by these ribs. And so this rough surface increases the surface for the heat transfer. So this is really beneficial. The second thing is that we have a different coefficient of thermal expansion for the aluminum and for the cast iron. So rough numbers, aluminum is around 22, 23 maybe, and the cast iron is closer to 11. So there is a double for the aluminum. We're going to go ahead and weigh this housing. So as you can see, it weighs around 571 grams. And it's 20 ounces or 1.258 pounds. So it's not much. 571 grams, basically a bottle of water. You know, they sell those waters right now, half a liter, that's about 500 grams. So that's all that is. This is the entire engine housing. I consider this a marvel of engineering. You know, a lot of these you can read about it online that it breaks and it's got all kind of problems. Obviously they didn't figure everything out. You know, the manufacturer is going to go ahead and spend 2 years developing this. And that's a lot of engineers, and it's a lot of testing, it's a lot of prototypes, and they got to a stage where they need to figure out if it's ready for the market. And what they do is they start selling it, and they are looking at the warranty numbers. If the warranty numbers are too high, they usually go and fix that particular problem. But I think what happens here is Ryobi is basically going to outsource this, or they outsourced this back in the 2000s. I'm guessing that's when this was developed, and they bought a product that was kind of meeting their specification. And so what the specification usually is, they want to have some kind of performance specification. So they want so many horsepower and so much speed and torque and weight and consumption. And the big difference basically between the 4-stroke and the 2-stroke trimmers, that the 2-stroke trimmers theoretically are double as power dense as the 4-stroke, because what happens is you got a piston moving up and down here in the cylinder, and for the 2-stroke engine you're working the fluid, in this case gas and fuel mixture. You're moving it or working on it above and underneath the piston. So what happens is, for one crankshaft revolution you're going to have all the 4 cycles, and for 4-stroke engines you got to go 2 crankshaft revolutions to do all those 4 cycles. And so for me, having it here, as a single piece, kind of 600-gram housing, it is amazing. So from engineering standpoint of view, just think about it. If you would have to design something like this, how would you do it? This is a backbone of a really complex system. We got 150 years in internal combustion engine development. If you go back to the steam engines, because when the gasoline engines came out, they already relied on a knowledge that was developed for the steam engines. And so this housing, it basically has to house the crank mechanism. So it has to be strong enough. So you can see these bores here. This is where the main bearings seat. So on the engine side here we have a big bearing, and I got all the parts there. I can talk about the size later. So we got a big bearing on this side, and then we have a smaller bearing on this side. Okay, so those two will house the crankshaft, and the crankshaft is going around, and the connecting rod is doing an alternating motion in and out. One end is doing an alternating motion, the other end is doing a rotating motion, and then the piston is going back and forth. And so when this engine is running, it is generating a tremendous amount of heat. Gasoline has a lot of energy. So when we burn that gasoline, it's going to generate a lot of heat. Now, a huge amount of heat is going to go through the exhaust port, but a lot of that heat is going to get trapped right here. Also, when the piston and the rings are moving in and out in a bore, they're going to generate heat because of friction. And so what the engine builders usually say is that the oil inside the engine does about 10% of lubrication and 90% of heat rejection. So we're actively using that oil in the system to reject heat. The oil is touching every little part inside that's encased in the engine, and it's picking that heat up, and as the oil travels inside the engine, it is depositing that heat to the parts that are cooler than the oil. So we have the normal heat transfer inside. One of the reasons I bought this is to figure out how they are solved the oil problem. So As you can see, this doesn't have an oil pump. So there's no oil pump attached. And yeah, the oil has to travel up here, cool this entire cylinder head section, and basically come back down. You know, you cannot have all the oil in a cylinder head. You cannot have all the oil inside the crankcase. So they came up with a really interesting solution. So what they have here is this is basically the crankcase housing. So this guy rests here. And this is the port through which you fill up the crankcase with oil. And of course, it has a dipstick somewhere around here. And you know, you got to put down the motor in a flat position and fill it up with oil. And then once you filled it up with oil, then you go and then you put this dipstick in. So that's the dipstick. Okay, so these are the markings on the dipstick. And then you put the dipstick in this hole, you screw it in, and that's how much oil you put in. It actually says right here, use 10W30 oil, do not overfill, see operator's manual. So this part, I can talk about this for a day, just this part itself. Okay, so you can see how lightweight it is. This is just basically plastic. So it's got this groove around the perimeter. So when you assemble this to the housing, there's a gasket, and it's gonna squeeze the gasket right here, and that's how it's gonna seal. Now on the inside it says PA46 GF50. So PA is polyamide, and 46 and GF50 is basically glass filled polyamide. There's some part numbers on it too. But you can see that, for example, this section right here is lightweight. So they added these ribs, they added the countersinks for the bolt holes. They are trying to minimize the material used on this one. And this guy is going to see the hot oil that the engine is basically running. So one way they cool the engine is basically the magneto, which is this guy. So it's a huge magneto. And if you look carefully, you can see it's got blades on both sides. Okay, so what these guys usually do is they spin with the engine, and when they are spinning with the engine, you know, in these channels, they're trying to throw the air out in this way, in a radial fashion. So when the air is traveling here, because it's trapped, the air is trapped between the two blades. And so when this guy is running, it's going to throw the air, and the air that left this channel is going to create a low pressure zone in the middle here. It's basically sucking air in from the axial direction this way and this way. Okay, so it's sucking in the air and it's throwing it in this direction, and as it's spinning inside the case, it's actually this way. So it's as it's spinning inside the case, the shroud, this shroud over the engine is gonna direct that airflow this way. So all the air flow that this impeller is generating is gonna scrub by the cylinder fins. And just look at those fins. You know, I've been in the industry for a while, and we have general guidelines from about the company where I'm working at and from the industry, from our suppliers. And they usually are telling us that the minimum wall thickness for cast aluminum parts are in the range of 2, maybe 2.5 millimeters. I can get a pair of calipers and we can measure that. And so this is my calipers. Okay, notice that the end is ground here. That happened because I dropped it once and these fingers, these measuring fingers broke. and basically I just ground it off, so I'm not going to be able to measure internal sizes with that, like internal diameters, but this part still works, and it's off by 50 microns typically, because this is my workshop and the temperature fluctuates between 40 Fahrenheit and 70 Fahrenheit. So if we look at these ribs, you can see their size is around 1.2 millimeters, and it's pretty consistent, so it's 115, 120, but that is remarkable casting these. You need huge pressures to introduce the aluminum into the mold, and so the aluminum is introduced, and it's running in a mold, and the mold is cool and the aluminum is cooling down in the same time, and you have to create a lot of pressure to push that aluminum in the mold before it solidifies. One more interesting thing that we can see here are these thickened areas. So these are what we call knockout pin areas. So you can see there are these flat sections. There are these sections also, which are round. There's one here. They are all over the body. So these are knockout pins. So what they do is when the part is molded or cast, basically it's a die casting process, these pins are going to come out and they're going to press the part out. So these are the areas where the pins are pressing the part out. Now a couple more interesting things. So I was talking about the oil circuit, and what these good people did is they created a special connecting rod. So that is the connecting rod. So the connecting rod is right here. The lower end is doing a circular motion, the upper end is doing an alternating motion. And if you notice, this is not typical, it's got a tail. So this tail section of the connecting rod, what it does, it is going to submerge itself into the oil in a crankcase, inside the crankcase. So this guy is sitting in oil, and every time it goes around, it is going to agitate the oil. So it is going to create an oil mist. And that oil mist is something that we can transmit or transport. And the way we do it is when the piston is moving in and out inside the crankcase, the pressure is going to fluctuate as a sine wave. And so when we have high pressure, that air with the oil mist is want to get out from here. So that's what these ports are doing. So what we have in a package here is a one-way valve. Okay? And this one-way valve is plumbed in here. And so what this valve does, it is going to allow the fluid to pass one way. When first I took it apart, I didn't really know what this is. And then soon I realized basically what I did is I blew into one side. You know, if we blow into the small end here, okay, right there. So if I blow into a small end, you can hear that it's whistling. Now if I blow into the long end, you can hear it's whistling, but it's not that strong. So it doesn't conduct this way, but it conducts this way. Okay? So when I took this apart, I noticed something else here. You can see in the top of the engine housing, so this is basically the cylinder head section, there is a port here, and it is machined. And if my zoom will be with me, you might be able to see that there's a lip inside. There's actually two lips and the two lips are pushing together. So this right here is a valve. And what that valve does, it will restrict the flow in one direction. So what I got is a piece of hose. So what I'm going to do is blow into this hole and put it close to this valve. So if I'm blowing air from this side, I got a restriction. It doesn't really go. But if we continue the hole here, this hole is drilled this way. So you can see this is basically the channel that houses that hole. Okay. So if we continue it and I turn it around, you can see that there's a little port here. So it's right under the piston. Okay, so I'm going to blow into that. And sure enough, you can hear the air is whistling. So what we got is we have a piston moving up and down. It's creating a sinusoidal pressure inside the crankcase. That air and pressure wants to go somewhere. So this port is one way to go. So once it's up here, the air that travels and has the oil mist in it, it will introduce the oil into this upper chamber. And then right here we have basically a sump. This is a sump for the cylinder head, and through this sump and this one-way check valve, the oil can come back to the crankcase. And so that was interesting for me because I am working on the engine that will have similar features, and so I wanted to look into this, how the industry figured it out, and what I can learn from this. So this is a type of competitive assessment or benchmarking. That's what the industry calls this. A couple other features on this housing that I want to point out. The first one is that if you look into the cylinder, trying to show it so that you can see, if you look into the cylinder, you can see that the valves, the axis of the valves are parallel to the cylinder axis. So typically if you have an engine, the valves would be tilted in a certain angle. So one of the valves would move this way and then the other one would move this way. Well, they cannot really do this on this engine because the valve seats inside here need to be finished. And by finished I mean they need to be machined and they need to be ground, or some kind of fine-tuning done so that the valves will sit in those seats properly. And so they cannot come in with a tool sideways like this, like on a normal cylinder head, because the tool just wouldn't fit. The cylinder is too deep for it. Okay, so the tool cannot come in this way because this upper section of the cylinder is not detachable. So their only ticket is basically to make the valves parallel to the cylinder axis. The other interesting thing I found is I was looking for seals right in this area. So that's where usually the valve seals are resting. Why do you need valve seals? Well, the valve is moving in this guide, so there's a nominal clearance between the valve and the internal bore, and there's going to be blow-by losses. So as far as the inlet goes, sorry, this is the inlet side, this is the exhaust. So as far as the inlet goes, you know, in the inlet we have vacuum, right? So when the inlet valve opens, it will draw in the fresh mixture, so that is vacuum. So if we have vacuum right in that cavity, that vacuum will draw in the oil mixture in here. So if the gap is too large, then we're going to start burning oil. On the other side, right here on the exhaust port, you know, on the exhaust port we have pressures, you know, 1 or 2 order of magnitude higher than on the inlet side, the vacuum on the inlet side. And so what that does, we would start blowing out exhaust fumes through this port here if there are no seals. And guess what? There are no seals. So this is just a compromise that the designers had made, because this would have made the engine too expensive. And so the other compromise, if you look into the cylinder bore, my lights are not helping me. I really want to show this cylinder bore right there. So if you look into the cylinder bore, you can see that there is an indentation, and it's a pretty big indentation. And so what it does, it will increase the volume of the dead zone. It's about 3 millimeters deep. And so when the piston goes all the way to the top, then you're going to end up with a volume of air. And if you take and get the ratio of the volume to the total volume when the piston is in the bottom dead center, then you're going to end up with that compression ratio. And so back when they started making engines, the compression ratio was around 1 or less. And then around the 20s it went up to, I'd say, 3. And then in the 50s it went up around 6 or 7. And then in the 80s and 90s it was around 9 or 10. And then really recently, just in the last 5-10 years, Mazda came out with engines that has really high compression ratio. So it's in a range of about 17. Now why is it important? Because compression ratio is directly proportional to the thermal efficiency of the engine. What is thermal efficiency? It's basically, I am burning some amount of fuel, and that fuel is generating heat. And what I'm doing, because at the end of the day this is a heat engine, I'm converting that heat into power through the mechanism inside the engine. And so if I have 100 amounts of heat and I'm basically wasting 90% of that, that's not a really efficient engine. So the compression ratio tells us how efficient an engine is. I think that's plenty of information, so we're going to stop right here. If you have any comments, please comment down below. See you next time. Bye.